Okay, so welcome to another lesson. So for this video, our topic will be improper integrals. So in improper integrals, so we have several cases. So we have two cases, okay, to be exact. So the first one is integrals having infinite limits, and the second case is for integrals whose limits are the interval of the limits is there is some discontinuity. Okay, so but we'll discuss that later. So but for this case, for integrals having infinite limits. Okay, so say for example, so we have here a very simple example. So you have the integral of dx over x to the power of 4 from 1 to infinity. Okay, so the integral of dx over x to the fourth from 1 to infinity. Okay, so whenever we have infinite limits, so what we are going to do is we will replace the infinite limit with any variable, okay, or any letter, and then outside the integral sign, so we write it as a limit, okay, where the variable that we have used to replace infinity, so will approach infinity. So that's a little complicated. It sounds complicated, but actually it's just very simple. So instead of writing infinity as the limit, so we will replace it with a letter. So say for example, we have integral of dx over x to the power of 4 from 1. So let's say, let's use a. Okay, so replace infinity with a, but outside the integral sign, so we will express it as a limit as a approaches to infinity. Okay, so that is the proper way to represent the infinite limits. Okay, so you should always replace it with whatever letter is on your mind, as long as outside the integral sign, so you express it as the limit of a approaches to infinity. Okay, so you can proceed as usual with the integration. So this will become this is power formula, I think. So we transfer x to the power of 4th in the numerator. So the limit of, so integral of x raised to the negative 4 dx from 1 to a as a approaches to infinity. Okay, so proceed with the integration. So its integration would be using the power formula, so it will be x raised to negative 4 plus 1. So x to the negative 4 plus 1 over negative 4 plus 1 from 1 to a as a approaches to infinity. Okay, so that will be, if we simplify this will be x to the negative 3 over negative 3, or it's negative 1 over negative 1 over 3 x cubed. Okay, from 1 to a as a approaches to infinity. Okay, so next is substitute the limits, upper limit minus lower limit. So the limit of So using the upper limit, it will become, substituting a to x, so it will become negative 1 over, 1 over 3 a cube minus, so since it's minus negative 1/3, so therefore it will become plus 1 over 3 times 1 cube. Okay, as a approaches to infinity. Okay, so using our differential calculus, so evaluating this limit, so the limit of 1 over, so the limit of negative 1 over 3a cubed as a approaches to infinity, its value approaches to, the value of this term approaches to 0. Okay, so because the denominator gets bigger and bigger and bigger and bigger, okay, so it's a divisor, so therefore, so if the divisor gets larger, so then its quotient, the whole term, its value will keep getting smaller and smaller and smaller until it reaches 0. So therefore, it's 0 and then plus, so this is 1/3. So therefore, our answer is 1/3. So therefore, the integral of dx over x to the power of 4 from 1 to infinity is equal to 1/3. Okay, so that's the proper way of representing infinity as limits. Okay, so all you need to do is replace it with another variable, okay, for which the limit of that variable will approach to infinity. Okay, so you may not appreciate this now, but for our for our next example, so you will appreciate why are we using limits. Why don't we substitute it directly instead? Okay. Okay, so for our next example, so we have this one. So evaluate the integral of dx over x ln of x from 10 to positive infinity. Okay, so again, in evaluating the integral with infinite limits, so we must replace the infinite limit with a variable and then express it as a limit. So we can express this as integral of dx over x ln of x from 10 to, say for example, p, okay, where the limit of this as b approaches to infinity. Okay, so the next problem is, how do we integrate this? Okay, so to integrate this is actually quite tricky. So, but this is actually just a natural logarithm. Okay, so if we let our u as ln of x, then its du is dx over x. Okay, so if we rewrite this, this is equal to the limit of integral of dx over x over ln of x from 10 to b as b approaches to infinity. Okay, so therefore, since the numerator is the complete differential of the denominator, so therefore this can be integrated using natural logarithm. So it will become the limit of, so integrating this will be equal to, this is in the form integral of du over u, right? So it will become ln of u. See, so it will become double ln. So ln of x from 10 to b as b approaches to infinity. Okay, so substituting the limits, so the limit of ln of b minus ln of 10 as b approaches to infinity. Okay, so substituting the limit, so b approaches to infinity, so what is the value of ln of b as b gets bigger and bigger and bigger and bigger? So this is still approach, the first term will still approach infinity. Okay, so ln of b is infinity, still infinity. So minus, so whatever the value of this is, ln of 10, so it's still infinity. Okay, so if upon evaluating and doing everything in your doing everything you can, but still you still arrive with the value of the integral as infinity, so then this integral is divergent. So the term divergent will be discussed further in our next lessons. So when we discuss about areas, okay, so what does divergent means? Okay, so in terms of the area. Okay, so we do have that. We do have those improper integrals where the integrals are divergent. Okay, so for our third example, so we have this one. So evaluate the integral of x e raised to the negative 5x dx from 0 to infinity. Okay, so again, first step, so first, before integrating, replace the infinity with another variable. So the limit of integral of x e raised to the negative 5x dx from 0, so let's say this time let's use c, as c approaches to infinity. Okay, so next, integrate this. So as you can see, we can integrate this by parts. Okay, so let's separate first. Let's integrate this first. So the integral of x e raised to the negative 5x dx. So integrating by parts, so using our general rule. So first, first priority in selecting u for substitution, so logarithmic. algebraic, correct? So sorry, logarithmic, inverse trigonometric, algebraic, trigonometric, and then exponential. So is that the right order? So layat. Okay, so logarithmic, inverse trigonometric, algebraic, trigonometric, exponential. So therefore our u here will be the algebraic part x. So u is equal to x. So therefore du is equal to dx. Our dv is e to the negative 5x dx. So therefore its integral is v is, so you have negative 5 here. So therefore to complete the integral we have to put negative 5 in the dx. So outside the integral sign we must put negative 1 over 5. So again, e raised to the negative 5x. To complete the differential, it should be negative 5 dx. Since we put negative 5, so outside put negative 1 over 5, so that we can integrate this part. So therefore it's negative 1/5 e to the negative 5x. So therefore the integral of x e raised to the negative 5x is equal to uv. So x multiplied by negative 1/5 e raised to the negative 5x minus integral of v du. So our v is negative 1/5 e raised to the negative 5x, and then our du is dx. So therefore this will become negative 1/5 x e raised to the negative 5x, and then plus 1/5 integral of e raised to the negative 5x dx. Okay, so I think this one is similar with this. Its integral is this. So therefore it will become negative 1 over 5 x e raised to the negative 5x plus 1/5. The integral of this is negative 1/5 e raised to the negative 5x. Okay, plus c. So therefore this will become negative 1 over 5 x e raised to the negative 5x minus 1 over 25 e raised to the negative 5x. Okay, plus c. So therefore you can replace this now with this, excluding the plus c. So let's just rewrite. So the limit of this from 0 to c, the integral of, oops, sorry, what is that? Integral of x e raised to the negative 5x dx from 0 to c as c approaches to infinity is equal to, so the integral of this is this, so negative 1/5 x e raised to the negative 5x minus 1 over 25 e raised to the negative 5x, okay, from 0 to c as c approaches to infinity. Okay, so next is substituting the limits. So upper limit is c, so the limit of negative 1/5 x, oh sorry, that is c, e raised to negative 5c minus 1 over 25 e raised to the negative 5c. Okay, so I think we're gonna be needing a bracket, minus, substituting 0, so negative 1/5 times 0 e raised to negative 5 times 0 minus, so that's 1 over 25 e raised to negative 5 times 0. Okay, close bracket and then close curly braces. So sorry, that was okay. So as c approaches to infinity, okay, so first one, so let's evaluate this. So this so we can see we have infinity multiplied by e raised to the negative infinity. So e raised to the negative infinity can also be expressed as 1 over e raised to infinity. Okay, and then it will become 1 over infinity. So limit of its value of 1 over infinity approaches to 0. So this will become infinity multiplied by 0. So it is still indeterminate. Okay, so for this one, this will approach to 0. Okay, and then obviously these two will be 0. So multiplier, this here we have a multiplier of 0. So this one will become 0. And then this one, so e raised to 0, that is 1. Therefore, we will have a 1 over 25 remaining here. So let's simplify this. So this will become, again, this will become 0. And then this will become also 0. Okay, because this will become 1 over e raised to 5c. And if c approaches to infinity, therefore, this will approach to 0. Okay, so simplifying, so where was I? So here, so we have the limit of, so this we can express this as negative c over five e raised to positive 5c as c approaches to infinity. This will become 0, this will become 0, and then this will become, so negative times negative, so plus 1 over 25. Okay, so the problem here is this one. Okay, so this, because this is indeterminate. Okay, so in this form it will become infinity over infinity if we substitute the limits already. Okay, so this will become infinity over infinity because e raised to 5c, as c approaches to infinity, therefore it's e raised to infinity. E raised to infinity is infinity. So this is still indeterminate. Okay, so luckily in our differential calculus, so we have already learned how to evaluate functions. Okay, whose limits are indeterminate. So one very useful rule was the L'Hopital's rule. Okay, so the L'Hopital's rule says that the limit of, say for example, we have f of x over g of x. Okay, so as x approaches to whatever limit, so that is equal to the limit of, you have f prime of x over g prime of x. Okay, so all we need to do is to evaluate the limit. So derive the numerator and then derive the denominator. So in this case, since our variable is c, we will derive the numerator with respect to c, and then we will derive the denominator with respect to c. Okay, so this now will become the limit of negative, so deriving the numerator, so derive c with respect to c, that is 1, and then deriving 5e raised to 5c, so we'll have 5 numerical coefficient, derivative of e raised to 5c, that is e raised to 5c times 5. Okay, so as c approaches to infinity, and then we have plus 1 over 25. Okay, so therefore if we simplify this, this will become the limit of negative 1 over 25 e raised to 5c plus 1 over 25 as c approaches to infinity. So with this form, so if we substitute, if we take a look at c, if its value approaches to infinity, therefore it will be e raised to infinity, and then it will become 1 over infinity. So the value as the value of 1 over infinity approaches to 0. So this will become 0. So plus 1 over 25. So therefore, the integral of what was our given, x e raised to the negative 5x dx from 0 to infinity is equal to 1 over 25. Okay, so comparing with our previous example earlier, so the example number 2, okay, so comparing with example number 2, so where was that? So this one, okay, so this term, okay, so there was no way for us to evaluate that that, what do you call this? So there was no way for us to express that into a term other than infinity. Okay, because this is not indeterminate. Okay, this is not indeterminate. Okay, not indeterminate. Okay, because it's ln of infinity. Ln of infinity is infinity. Then ln of infinity is infinity. So therefore, we know that the result will be infinity. Okay, unlike here. Okay, so unlike in this one, so this one is indeterminate. Okay, because this will result to infinity over infinity. Okay, and infinity over infinity is indeterminate because we don't know which infinity is larger. Okay, so infinity is used to it is used to express very large numbers. Okay, but it is not a number itself. Okay, so if you have watched the movie, I forgot what that movie was. I think it was The Fault in Our Stars. So starring the star of the Divergent series. So some infinities are larger than other infinities. Okay, so it doesn't mean they are both infinity, doesn't mean that they are equal. Okay, so therefore we don't know, okay, which one of them is larger. So if we divide them, is their value greater than 0 or less than 0, or sorry, greater than 1 or less than 1? Okay, because we don't know if they are equal, if the numerator is larger than the denominator or the denominator is larger than the numerator. So there is no way to determine its value. Okay, so that's why in this second example, in this third example, so we use the L'Hopital's rule. Okay, so to evaluate the limit. Okay, so up next is case 2 for improper integrals.